the different types of reactions, and we'll get back to doing conversions with them in chapter 8. So let's just talk about what a chemical reaction is. All right, so chapter 7 is where I'm starting now. This is chemical reactions. All right. There we go. All right, chemical reactions. What's a chemical reaction? All a chemical reaction is, if I give the book definition, all it really is a process in which one or more substances are converted into one or more different ones. Remember when we talked about changes, physical changes versus chemical changes? We said if it's a chemical change, it's just saying it's a chemical reaction is occurring. So just remember, all a chemical reaction really is a chemical change. You start off with one substance, a change happens, and you end up with a different substance. All right, so the way we express chemical reactions or chemical changes, we use chemical equations. And a chemical equation starts off with reactants that lead to products. So the reactants are basically what we're starting off with. I'm going to say it's our starting material. And then the products are end material. Now, just like equations in math, when we write a chemical equation, the number of things or substances on one side has to equal on the other side, meaning we think of this arrow sign like an equal sign. So the number of atoms on the reactant side has to equal the number of atoms on the product side. So let me give you an example of what I mean. Let's say, for example, we're talking about a combustion reaction of methane gas. Remember, methane gas is the gas that we use to heat up our homes. The gas, if you have a gas stove, it's the gas that comes through the pipes that heats up your stove. So methane gas has a formula CH4. And this little subscript I write here, this G, stands for gas. And we're gonna write all our states of matter like that. So for instance, I'm saying G equals gas. When I write an L, that means liquid. If I write an S, that means solid. And do you guys remember what AQ means?
Aqueous?
Aqueous.
S.
Yep, aqueous. And remember, all aqueous means is it's dissolved in water. So for instance, if I put salt, like if you go get salt out of your cabinet, pour some water in it, you know the salt is going to dissolve in the water. That's an aqueous solution of sodium chloride. All right, so when we talk about the combustion reaction of methane gas, so what ends up happening is that if I have methane gas and then I add oxygen gas to it, and remember, oxygen is one of the 7 diatomic molecules. So whenever we write it, we have to write O2. Whenever we write it by itself, or we call this elemental oxygen gas, we write it as O2 because it doesn't exist as just plain oxygen. So oxygen gas, they react together, and with some energy, they form carbon dioxide, CO2, and then a subscript G, plus water vapors, H2O, and it's a gas as well. So I'm saying water vapors and not liquid water. So this is a chemical equation that expresses the reaction of methane gas in the presence of oxygen gas. Now, this chemical equation, remember I said the number of atoms on each side has to equal each other, just like any equation in math. We have to use what is known as coefficients to balance the chemical equations. So the coefficients are just whole numbers that we put in front to multiply each substance so that they can all balance out. And the way we figure out what our coefficients are going to be is I say in this class, we have simple equations. We're just going to go from left to right. So meaning, if I look at carbon on the reactant side, I see that I have 1 carbon. If I look at carbon on the product side, I see that I have 1 carbon. So if I kind of make a list of everything I have. So if I start, this is the reactant side. If I look at my carbons, on the reactant side, I have 1. On the product side, I have 1. So my carbons are happy. Then I'm going to go to hydrogen. It's the next element that I see. Hydrogen. How many hydrogens do I have, guys, on the reactant side?
4.
4. I have 4. We see from this subscript, I have 4 hydrogens. But if I look on the product side, how many do I have? I only have 2. Thanks, Crystal. I only have 2. So these are not equal. I need to make them equal. To do so, I use a coefficient of 2, and I'm going to stick it here. And it's like I'm multiplying this water times 2. When I multiply this water times 2, I'm saying 2 times H2 as well as 2 times O.
How is that different than writing H2O in parentheses with a subscript of 2?
Good question. So in this case, if I change, remember, if I say H2, let's say you're saying like this?
Yeah.
Okay, we usually write the subscripts when we're trying to write out the formula. The subscripts are for the formula. When we're trying to say how many of each molecule we have, we got to write it in front so we don't get confused. Another thing that you guys like to do is say, okay, I need 2 more, and sometimes you just stick a 2 here for the oxygen. This is a different formula than water. This ends up being hydrogen peroxide versus water. So instead of just sticking it here and confusing it with hydrogen peroxide, that can be a little confusing is all I'm really getting at. So when we write this subscript, it's usually to say, okay, you know how we're saying, remember when we did our ionic compounds and we need our charges to balance out? We write the subscripts to say how many of each element we need, not how many of each molecule we need. Did that answer your question, Avery?
Yeah, it did.
Okay. So in this case, we're only going to write the 2 in front of the molecule, and we call these coefficients versus writing it as a subscript. If I change my subscripts, it's going to change the formula and it's going to be a different compound. So remember, H2O2 is hydrogen peroxide versus water. We can drink water and be fine. We need it to live. Drinking hydrogen peroxide would kill us, if we drink too much of it. All right. So good question though. I'm just going to scratch this out so it doesn't get confusing. All right, so now I put the 2 in front of the water. I now have 2 times H2, which makes it 4 hydrogens. And now I have 2 times O, which makes it 2 oxygens. So when I get over here back to my oxygen, because I'm satisfied with my hydrogens now, if I go to the oxygens, you see I have 2 oxygens here, but now on the product side, I have 2 oxygens from this H2O because I multiplied it times 2, but I also have another 2 oxygens from the carbon dioxide. So total, I have 4 oxygens. So what do you guys think I need to do to make these equal?
Put the 2 in front of the oxygen on the left.
Exactly. Just stick a 2 here. Now I have 4 oxygens and I'm happy. And this is really as simple as balancing equation gets. Like, this is pretty much what we're going to be doing. Some of them we have to think a little bit harder, but it's not impossible. We can balance equations. Let's do an example where you guys balance it and see if we all get the same answer. All right, so let's say my example says I have silicone dioxide plus carbon. So this one's a solid, this one's a solid. Reacts to form silicone carbide plus carbon monoxide, which is a gas. Let's see if you guys can balance this equation properly, and then we'll go over the answers. So spend a second and try to balance this one. All right, guys, let's talk it through. You guys got an answer?
Yes.
All right, let's talk it through. So if I go from left to right, I'm starting with silicone. So how many silicones do I have if I write it out here? Silicones, how many silicones do I have?
One.
I have one over here. How many do I have over here?
One.
One. All right, so silicones are happy. I then go to oxygen. How many oxygens do I have on the reactant side?
Two.
Two. We see this subscript 2 right here. We have 2 oxygens. Now, when I get to the product side, how many oxygens do I have?
One. Only one.
We only have 1. Okay. So what should I do, guys, to make this 2?
You put a 2 in front of a C.
Multiply by 2, put the 2 in front of the C or the carbon monoxide. So remember, this 2 is going to say to here and to here. Right? All right, so now on the product side, I have 2 oxygens. Okay, so they're happy. Then I go to the carbon. How many carbons on the reactant side?
One.
1 carbon. How many carbons on the product side?
2.
3 carbons.
How many 2 or 3?
3.
3. So we have 2 from here, and then we have another 1 from here.
Oh, okay.
So we gotta remember to add them together. So if they're on the same side, it's like they're on the same side of the equal sign. We want to put them together and we say there's 3 of them over here. What should I do to make 3 on the reactant side? Multiply by 3, there's now 3. So in this case, even though there's not a 1 right here, we just assume there's at least one of them because it's written down. So it's like this says 1, 3, 1, 2. Okay, let's do another one. Anybody have any questions before I keep going? Any questions before I go to the next one?
No.
All right, let's do another one. My next example, now I'm gonna do one that has a polyatomic ion. All right, so let's say we have strontium chloride and it's aqueous plus lithium phosphate and it's aqueous. They react to form strontium phosphate plus lithium chloride. And these are all, this one's a solid, this one's aqueous. All right, let's talk through this one together. When we have polyatomic ions, so the polyatomic ion that I'm referring to is phosphate in this case. Remember, if you don't remember the polyatomic ions, you got to reference this sheet. The polyatomic ions, phosphate is right here, PO4 3-. So when you have a polyatomic ion like phosphate, you group them together and you don't break them apart as long as you have one on both sides of the arrow sign. Meaning, I wouldn't say that, oh, I have 1 phosphorus and 4 oxygens here. I'd say I have 1 phosphate group, and then on this side, I have 2 phosphate groups because there's a subscript of 2 here. It'll work out just fine if you break it apart, but it'll just take you longer. The easier thing to do is keep the phosphate group together or all the polyatomic ions together as long as you have 1 on both sides of the arrow sign. So that way you can say, oh, I have 1 versus 2. I just need to multiply this by 2. All right, so let's go from left to right. If we start off with strontium, I got 1 strontium here. I have 3 on this side. What do I need to do, guys?
Add 3.
Add a
Multiply
three.
by 3.
When I multiply by 3, how many chlorines do I have now?
6.
6.
I have 6 chlorines now. So then on the product side, how many chlorines do I have?
1.
Just 1. So what should I do?
Add a
Put a
6.
6.
Put a 6 here because I want 6 chlorines. Okay, so then I go to lithium. I have 3 lithiums, but let's look on this side. How many lithiums do I have?
6.
I have 6, so what should I do to make this one 6?
Multiply by 2.
Multiply by 2, perfect. And then now, how many phosphate groups do I have?
1.
Try one more time.
2.
We have 2 because we got to remember this 2 goes here and here.
Yes, yes, yes.
So I have 2 phosphates, and look on this side, I already have 2 phosphates, so I'm satisfied.
Okay, okay.
All right, so I'm going to put a star here that says, don't break apart polyatomic ions. If there's one on both sides. I'll say both sides of the arrow sign. All right, so a question comes up a lot. The question says, let's sum the coefficient. Let's say the next question is like a part B from this equation. After you balance the equation, it says sum the coefficients. And remember, the coefficients are the numbers out front that we multiplied each substance by. If I were to sum the coefficients, what do you guys think the sum is? Like if I were,
11.
12.
okay, I see
12.
a 12, I heard an 11, I see an 8, 12, 11. Okay, we're going back and forth between 11 and 12. All right, so this one's kind of like a trick question. That's why I'm telling it to you now. So if it comes up on a quiz or a test, you don't get caught off guard. When I sum the coefficients, we see there's a 3 plus 2, that's 5. And then you see the 6, you add it up, it's 11. But then you got to remember, this is an assumed 1. So if you sum the coefficients, it'd be 12. So don't forget about that assumed 1. Even though it's not always written there, you don't have to write that 1. You just have to remember it when you have a question like this. Does that make sense, guys? Give me a thumbs up.
Yes.
All right, cool. Let's do one more example and then we'll talk about the types of reactions. Let's do an example where you guys have a polyatomic ion. Let's see if you guys can set this up. I'm not going to write the states of matter so I don't run out of room when I write my equation out. So let's say I have lead 2 nitrate. Looks like this, plus sodium chloride. Reacts to form lead 2 chloride plus sodium nitrate. You guys balance the equation properly. And let's see if we all get the same thing. Okay, guys, let's talk through it. You guys got an answer?
Yes.
All right, let's see if we get the same thing. We have one lead, so we're happy with the leads. How many nitrates do we have? We have 2 nitrates. How many nitrates on this side?
One only.
Okay, so what should I do?
Multiply by 2.
Put a 2. All right, so then I get to the sodium. How many
Only one
sodium?
sodium.
1 sodium. How many sodiums on this side?
2.
So what should I do?
Multiply by 2.
How many chlorines do I have?
2.
And how many chlorines do I have on this side?
2.
So did we all get this? Did we all get 1, 2, 1, 2?
Yep.
Yes.
Yes.
Okay, so it's making sense, guys? All right, good. That's about as hard as it'll get. Sometimes you got to go back and change things. So let's say I changed this to a 2, but it affected something else. I got to go back and fix something on the reactant side, but it's never meant to be that difficult. If you're spending 10 minutes trying to balance an equation, you did something wrong, okay? So don't spend such a long time trying to balance it. Just pause, take a break, come back to it, and maybe you'll see something different when you look at it again.
Sum
All
of
right,
will be what? 5?
Say it again.
Sum will be how much? 5?
Oh, the sum, yep, so let's see. 1, 2, 1, 2, looks like 6 to me. So 1 plus 2 is 3, and 1 plus 2 on this side is 3. The sum of the coefficients would be 6. All right, so let's keep going to the different types of reactions, and then I have a worksheet and we're gonna do some practice problems. So we have the different types of reactions. Let me start a whole new page for this. So reactions can be grouped in different ways. I'm gonna start off by first grouping them on what their atoms or groups of atoms are doing. So types of reactions. So this is grouped on what atoms / groups of atoms are doing. All right, so when we talk about the different types of reactions, let's start off with first one. It's a synthesis reaction. Synthesis reaction, another word for that is combination. We say synthesis or combination. Synthesis just means we're making something, we're synthesizing something. And a synthesis or combination reaction, the way it looks is we say we have substance A plus substance B reacts to form substance C, a whole new thing. Synthesizing means we're making something new. Combination means we're combining these two things to make this. Another way of saying C is just it's A and B combined. So let me give you an example of a synthesis reaction. An example would be, let's say we have, for instance, sodium plus chlorine gas. So this is a solid, this is a gas. React to form sodium chloride. We call this synthesis. We're making sodium chloride. We're saying sodium is combining with chlorine to make the formula NaCl. Notice that this is Cl2, but when it comes together with sodium, it's just one Cl. And that's because this is an ionic compound. And remember, we just want to balance the formula. So sodium has a +1 charge, chlorine has a -1 charge. So the formula just looks like NaCl. To take care of these two chlorines, we put the coefficient in front saying we need 2 sodium chlorides to balance everything out. All right, so another example of a synthesis or combination reaction, it doesn't have to just be one element plus another element. We can say one compound, such as water, one compound plus another compound, which is sulfur trioxide, react to form sulfuric acid. This is still compound A plus compound B, or substance A plus substance B, reacting to form a whole new substance.
How do you know if it's gonna be an aqueous or solid or,
We're gonna go over that towards after
Okay.
we talk about the different types of reactions.
okay,
And most of the time in this class, the equation is just gonna be given to you and it's already telling you what type it is. But there are a few rules that we're gonna go over. If we don't get to it today, we'll do it tomorrow. All right, so this is combination. That's the first type of reaction. Second type of reaction is a decomposition. A decomposition is when something decomposes or breaks down. So it's the opposite of the combination or synthesis. So now we have our substance C breaking down to A plus B. And remember, C is just like saying A and B combined. So an example of this type of reaction is simply saying if I have water and I break it down to just hydrogen gas and oxygen gas. Another example of a decomposition reaction is if I have one substance such as calcium carbonate. And I break it down to just calcium oxide plus carbon dioxide. So I just want to show that it's not just saying I have one element plus another element. I can have one substance or one compound plus another compound. So remember, this is just the opposite of the first one. I also can have what is known as a single displacement reaction. Single displacement. And a single displacement is saying one thing is being displaced or one thing is being replaced. So I'm saying if I start off with A, oh, let me write this in green so not to mess up the scheme. If I start off with A plus BC and A replaces B. So now B will be by itself and A will go into the compound as AC. So what's happening is my A and my B switch places. And an example of this type of reaction is like saying I have solid zinc plus copper 2 chloride. And so in this case, zinc is my A, my B is the copper, and my C is the chloride. So my zinc and my copper are gonna switch places. And when they do so, I end up with copper by itself plus zinc now being in a compound with chlorine. And let me know if you guys have any questions. And then I have the type of reaction that we call a double displacement. So a double displacement is similar to a single displacement, but this time I have two compounds. So I have an AB plus CD. And what ends up happening is, once again, my A is gonna switch places. My A and C are gonna switch places. So in this one, I had one compound in an element. Now I have two compounds. My A and my C are gonna switch places. So now I say A now goes with D, and C now goes with B. And an example of this type of reaction is, I'm saying, let's say I have silver and the nitrate ion. So silver nitrate. So I'm saying silver is my A, nitrate is my B. I reacted with sodium chloride, where sodium is my C and chlorine is my D. When these two are mixed together, my silver and my sodium are gonna switch places. And when they switch places, I now have sodium, or so I'll say silver going with chlorine. So silver, I now have the A and the D together. And then my sodium is gonna go with the nitrate. This is my C, this is my B. Do we see this, guys? Like, is it making sense what I'm doing with these types of reactions?
Yes.
Yes.
Okay.
I just don't get decomposition.
Decomposition, let me go back up to it. You get combination? Do you get the first one?
Yes, I do get the combination one, yes, so it's
All right.
Okay,
So you're just adding two things together and making a whole new substance. Decomposition is the opposite. We're just taking, it's like saying if I took sodium chloride and broke it down to just sodium and chlorine. So I just gave different reactions. I'm saying, okay, water, I'm gonna break it down to what it's composed of, hydrogen and oxygen. In this case, it's calcium and carbonate. So I break it down into we can think of calcium carbonate, and you would think it would break down the calcium and then the carbonate ion, but that's not how it breaks down. It breaks down the calcium oxide and carbon dioxide. So think of it, I like to think of it as like, how many plus signs do I have and where are the plus signs? If I have one substance and then I break down to this plus this, it's decomposition. Or if I say this plus this makes something by itself, it's gonna be a combination. So I kind of think of like the plus signs when I'm looking at these two. In the other cases, we just have to recognize if I have something by itself plus a compound, it then switches places, and then I have two compounds together that are mixed together. I'm gonna get two different compounds.
Okay.
It can be with polyatomic ions also, right?
Yep. All right, so let's look at this worksheet that I posted. So let's go to the one that says, I don't know how.
Professor, one question I have more.
Yep,
We need to balance it also if we need.
yep, these are already balanced. I balanced all these already. But in general, you have to make sure your equation is balanced. You always have to make sure it's balanced because it's just gonna affect how we do our calculations. We aren't gonna get to the calculations until next chapter, but for right now, we're just gonna learn how to write the equations and balance them properly. It's kind of like,
Professor,
mhm.
real quick, I got a question. So it's 4, 3, 2, and then which one was 1 before decomposition? I was
Here you
trying
go.
to see if I wrote that down.
Combination.
Sentences. Hold on, let me see if I wrote that. Yeah, I wrote it down. Thank you.
Okay, no problem. All right, but yeah, we always have to make sure our equation is balanced. So let's pull up this worksheet.
Quick question on the double displacement.
Yep.
So you said like the silver and the sodium switch,
Mm-hmm.
but then on the right side, it's really just the chlorine and the NO3.
You can think of it either way. Because look, I did switch places with the silver and the sodium. You can think of it as the nitrate and the chlorine switched, or you can think of it as the silver and the sodium switched. So it's the same thing. If you say silver replace sodium, that means silver now goes with chlorine and sodium now goes with nitrate.
Okay.
Yeah, it doesn't matter how you think of it. And guys, you know, if I have these plus signs here, it doesn't matter which one you write first. So I could say BC plus A, or I could say CB plus AD. It doesn't matter which one you write first. It's like saying 1 plus 2 or 2 plus 1. They still both equal 3. So I only wrote it out this way, but if you rearrange which one you added first, it doesn't matter. Any other questions? Okay,
No.
so let's pull up this worksheet and let's do a few practice problems and then we can take a break. So on this worksheet, it says we're gonna balance the following equations and then we're gonna classify them as synthesis, decomposition, single displacement, or double displacement. So this is what we have to do all the time. We always have to, anytime we have an equation, we have to make sure it's balanced. And after we make sure it's balanced, we can classify it as such and such. So let's do the first one together. And then I'm gonna go down here and do these together too. All right, so let's do the first one together. If we look at it, we have iron plus silver sulfate reacts to form iron 2 sulfate plus silver. All right, so let me go ahead, let's balance this one first. If we go from left to right, on the reactant side, I'm gonna start off with my my iron. I have 1 iron here. I have 1 iron on that side. I'm satisfied. I then go to my silver. I have 2 silvers. What do you guys think I need to do over here?
Add a 2 in front of the 8.
I had a 2, Sandu, I see you mouthing the words.
I'm sorry.
Huh?
Oh, no, sorry. No.
Only
right.
one silver or what?
So on the worksheet, it says Ag2. So on the product side, I need 2 silvers. And then I get to sulfate. How many sulfates do I have on the reactant side?
1.
1, and how many do I have on the product side?
1 as well.
So we're satisfied with the sulfates. This is the balanced equation. So can we look at this and look through the 4 different types I just gave you guys and see what type of reaction you guys think this is?
Single displacement.
Do
I
we
agree.
agree that it's single displacement?
I think so too.
Yep, let's look at it. We have an element by itself, which I will call this is my A. And then we have B, C. And now they switch places. So now I have, what's this, B out here, and then I have AC together. So this is what I'm saying. It doesn't matter what order you write it in. It's just that one's by itself and you switch which one is by itself. So yeah, we say this is a single displacement. So I'm just gonna say single here. All right, guys, let's do up to number 5. Let's go ahead and do up to number 5, see if we can balance it pretty quickly. See if we can see what type of reaction it is.